Hello everyone and welcome to ML Done. In the last video we downloaded a Brain MRI image dataset for brain tumor detection. Now in this video we're going to learn how to read that data. Okay, so let me just go back to our Jupyter notebook, and just as a reminder, so this is the type of directory structure that we have. So under the folder data I have all of the images under another folder called brain tumor dataset, and under that you've got no tumor and yes tumor classes, right? I mean, and under each one you've got your images, right? So that's the structure, and this is my the script that I'm running, right? Now let's start by, let me make this a little bit brighter so I can read properly. Great. Now let's make this a markup or markdown, sorry, cell, and let's call this reading the images. Yeah, so let's just read in the tumor images first. So I'm going to create a list, right, called tumor, right? And then obviously I'm going to have access to the directory in which the tumor images are, well, reside, right? So let's just create a variable called path, right? Now, as I said, all of our data is under this data folder, right? And the data folder resides in the same directory as our notebook. Now, the way that, at least in Windows, that you can specify this directory and from this directory go into this folder or that folder, whatever it is, the way to do it is with the dot sign, right? So that dot means this directory, and in Windows you use forward slashes, right? And then it means in this directory go into, well, it's the data folder, and under data folder you've got brain tumor dataset, and under that we'll have to go under the yes folder, right? Remember, we want to specify the directory to the brain tumor images. So I'm just gonna copy and paste this path over here, right? So under data, under brain tumor dataset, under yes. Now, one thing you need to notice is that over here, under yes, we've got many images, right? And it's a little you might find this tricky. Okay, how can you read you know, each and every one of these JPEG images? Now the way you can do this, again thanks to Python, and in particular the glob package, you can actually go through this particular set of directory, and under the directory yes, you can say, okay, all the images with the extension JPEG, right? And all, that's keyword all, you can show it with a star, right? With a wildcard, and then .jpg, right? So this means that in current directory go under data, and then go under brain tumor dataset, go under yes, and in that directory, whatever JPEG image you find, I'm referring to all of them with this string. Okay, so now we have the path variable to our tumor images, right? Now obviously I'm gonna have to iterate through this directory, right? So I'm gonna create a loop for, and then I can use whatever letter I want. I'm just gonna use F because F is short for file. For F in, so remember we have imported the glob package, right? Let me just run this bit. Yeah, we have imported the glob package, right? And we said that glob will allow you to walk in a directory and then, you know, specify whatever you want to do with each and every one of those files. And this is just one of the ways that you can iterate through a directory. There are many different ways of doing that. This is just one of them. And glob has a sub package called iglob. And iglob, what it takes is the directory or the path of interest, which in our case is the path variable that we have already defined. Remember, path points to the directory of all of the JPEG images under yes folder, which means all of the tumorous images. Now, at every iteration, F becomes one of these files, right? One of these JPEG files. So what you can do is, I'm going to create an image, and you remember that the CV2 is a package that we're going to use to actually read in an image. CV2 gives you a nice an ability to read multi-channel images, like channels that have the red, the green, and the blue channels, or images that are totally grayscale, and they might even have only one channel. And that's still fine, right? So CV2 gives you that ability, and it actually matters, because sometimes what you want to do is you want to extract each channel separately. In certain machine learning applications, that type of pre-processing is actually, I mean, can be handy. I mean, I'm not making a big hassle out of it, but it can be handy. So again, this is one of the ways that you can read in an image. So this is just one example of doing that. Okay, you're more than welcome to try different ways. So CV2 has this sort of a sub package called imread, right? So by the way, so when I put dot imread, when I press on tab, it gives you the options, right? By pressing enter, I'm choosing imread, right? And then you put your F there, right? In other words, at every iteration, F becomes the name of a particular JPEG file, right? So maybe 1.jpg, 2.jpg, 3.jpg, and at each iteration, this F points to one particular JPEG file, right? So at every iteration, F becomes a path to a given JPEG file, and CV2.imread gets that path and reads the image and puts it in the img variable, right? Now, so now we've got the image, right? So I'm just gonna make it a little bit simple here. So we can simply append this image to our tumor list, right? So tumor, which is our list, dot append img, right? So this loop keeps happening until you get to the end of all of the JPEG files under that directory, and at every iteration you will have added that image to your tumor list, right? So if I run this, okay, great. So now you've got all of these images in this tumor list, right? So if I actually take the length of my tumor and run it, so we've got 154 images. In particular, they are tumorous images, right? Now, I want to show you something. This is interesting, and this is an example as to why pre-processing matters, while getting comfortable with the data matters, right? So I'm going to iterate through this this list. Let's call it img in tumor, right? And what I'm going to do, I'm going to print the shape of each and every one of these images in our tumor list, meaning that what's the height of the image, what's the width of the image, and if the image is multi-channel, how many channels do we have? Typically you either have one channel or 3 channels, and the 3 channels, as I said, are for the RGB images, which is in our case, that's in our data set, that is the case. We have RGB, red, green, and blue channels. So that shape returns height, width, and the number of channels here, right? So at every iteration, we get one of the images in our tumor list and print out its shape. Now, when I print it, you notice something immediately, right? You did, right? So first and foremost, the number of channels is appearing at the very end, right? And you can see that we've got 3 channels across the board. But more importantly, and I would say more disturbingly, the height and width of your images, they're not equal, obviously, right? You've got different ranges. You've got height or width, whatever it is, of 218 all the way to 1,200. Same story for the width. You've got 1,061 here, and then you've got 194 there. It's a mess, right? And why this matters, first of all, you want to make the size of the images or your input data, because you're going to use this with a machine learning algorithm, in particular a neural network in our project, right? So you have to fix the length and the dimension of your images, right? Or of your data. That's how you deal with neural networks in particular. The dimensionality of the data has to be fixed, right? So it shouldn't be the case that your x1 has a certain dimension and the x2, which is your second input data, would have a total different dimensionality. All of a sudden you have 3 channels and then 1 channel and then 10 channels. That's not how it works, right? So you have to make sure that you are consistent dimension-wise across your images, right? Now, the other thing that might be worth mentioning is that sometimes when you read these packages to read in the images, sometimes if you have multi-channels, which is in our case, certain packages will treat those channels in a different way, meaning that they might read them in different order. So BGR or RBG or whatever, or maybe RGB, right? So just to go with the convention, and also I'm looking for an excuse to show you more stuff about CV2. I just wanna make sure that the order of those channels are exactly like RGB, right? Doesn't have to be, right? But it's just a convention, and you see that a lot in machine learning and in the world of computers, that sometimes something is not really that necessary, but because we want to be consistent with the way we do things worldwide, we just follow a convention. And RGB, that particular order, is a convention, right? So I just want to show you how you can do it. Now, we have used a resize and we've changed the size. Now, again, CV2 has a nice ability called split, right? Now, when you pass your image into this particular function, what it does is it returns a list, right? And the order, it returns 3 values. You can put them in a list or just simply 3 variables. Now, the order is BGR. I mean, I'm just putting these names for the variables just to give you a hint as to which channels are being returned by the dot split functionality. So the blue, the green, and the red channels are being returned, right? Now what I'm going to do, I'm going to put them in the right order, right? RGB, and then, well, not the right order again, the conventional order. I'm going to put them back into RGB order, merge them together, and put the result back into image, right? So what I'm doing, I'm grabbing this image, splitting the channels, reordering the channels, and putting them back into the original image, right? Now we have a multi-channel image with the same order that we want, right? Which is RGB. Now again, CV2, we're going to use CV2. The function is called merge, and under merge you pass these channels in the form of a list, right? So we'll have R, G, and B, and you put it back into your image, right? Again, remember, these 2 steps are not really essential, but again, conventionally correct, right? So that's what we did, and now we've got the tumor images and everything seems fine. Now let me run this again. Hopefully all is good still. Okay, great. So everything ran, everything was perfect. So we're grand with that, right? By the way, for those of you who are not from Ireland, when people in Ireland say that's grand, it means that's okay. And I know that in America that is not an expression, but I just said it without even thinking, because I've been living here for a few years now. Anyway, now so now we have a way to read images, to resize them, to split them into individual channels. And remember, each one of these channels, by the way, is a 128 by 128 image, right? And when you stick them together, you will have 3 images, each of which is 128 of dimension, 128 by 128. And because you have 3 of them, that is why when you look at the shape of the entire image, you get 128 by 128 by 3, meaning that you have 3 channels of the same 128 by 128 dimensionality, right? So all is fine. We just made it work. Now, one other thing, remember, we also have healthy images, right? So let's create another list. Let me just to be a little bit tidier, let me just erase that. I'm just going to copy and paste this, but this time we have, say, let's call it healthy images, right? But this time it's the same structure of the directory, but this time we call it no, right? Because if you remember, again, we have the healthy images under no folder, right? So read them, and here, instead of tumor.append, we'll have healthy.append. So we'll do exactly the same thing that we did for the tumor, right? Now, again, if you go healthy, maybe let's call length of healthy. You have 91 healthy images, right? Okay, perfect. So now we finished with all of that, right? So now we've read the data. Last step is to convert all of these lists into Numpy arrays, right? For a very good reason that Numpy is just magical. You always want to have Numpy stuff. Now, the way to do it is, I'm going to say healthy equals from NP. Remember, Numpy, we have imported it as NP, so we can use the keyword NP to use Numpy everywhere. So Numpy array, we're converting something into a Numpy, and that something is going to be our healthy list. So after we convert it, we put the result back into healthy, right? Now we're going to do the same, only this time it's going to be with our tumor list. Yes? Great. Now if I run this and run that, perfect. Now here's the thing. This is one of the good things that you want the first what's the thing, what's the word, one of the benefits that you can see from Numpy immediately. So tumor is a Numpy array now, right? I'm going to do something that you couldn't have done with a list. Simply tumor.shape immediately gives you the shape, right? There is no such functionality with lists. So this is a teeny tiny benefit that you can immediately get information about the structure of your file. And now what does this thing tell you? It says that we have 154 data points, right? And each data point happens to have 3 dimensions. The first dimension, you have 128 values, or let's say 128 say rows. You got 128 columns, so that becomes your image. And by the way, we have 3 channels of those, right? So in other words, if I want to make it a little bit more intuitive, we have 154 images, each of which has 3 channels, and in each channel you got a width and a height of 128, right? Now, there is one thing that I want to, maybe I'll do this later on, but typically the way you treat this channel sort of dimension, typically what you do is you reshape this array into a shape where the number of channels come first, and then the height, and then the width or the height, doesn't matter, but the number of channels tend to be before you hit your height and width. Okay, so this is a little bit non-conventional, but we're gonna take care of this later on. But that's not the point of this particular session, right? So, and you can also do this with healthy.shape, right? Just to give you an example. So you have 91 healthy images, each of which has 3 channels, and each channel has a dimension of 128 by 128, right? Perfect. Now, you can also create another variable, let's call it all, maybe with capital, yeah. You can put it anywhere, anywhere you want, doesn't matter really. Now, what you can do, you can concatenate all of these images together. So np.concatenate, then you can put your healthy and tumor images together, right? Now, if I printed it out, what happened here? So it says only integer scalar can be converted to scale. Oh, sorry. So you have to actually put the Numpy arrays that you want to concatenate into parentheses. In other words, in a more Pythonic way of talking, you pass in your arrays in a form of a tuple, right? So that's the only thing you need to do here. Now, if I run this again, great. So if I take a look at, so again, the output of NumPy concatenate is another NumPy array, right? So if I look at the shape of that, so you got 245 images, right? So remember that we had, what was the dimensionality of this guy? Right, it was 91, and the dimensionality of the tumor NumPy array is 154, right? So if you sum these up together, you should get 245, right? So 154, I'm just too lazy, I'm just gonna sum it up with Python. Now I'm using Python as a calculator, and voila, you got 245 images. Great, perfect, great stuff. Now, so I think we're done for today's video. I'm just going to relax a little bit. I'm getting a little bit too hyped up. Yes, so perfect, we're grand. So in this video, what we did was we went through our data set that we had downloaded from Kaggle, and we read in all of the tumors and healthy brain MRI images using a for loop, using the glob package, and we walked into those directories and grabbed all of the JPEG files. What we did was we took a look at the dimensionalities of those images, and we realized that they're all over the place. So we resized each individual image, and then we followed the convention of making sure that the order of the channels are red, green, and blue. We didn't have to do these two steps, but just following the convention. And then we used two lists to actually store each and every one of these images, and then we converted them into NumPy arrays, and then we concatenated them together to have one unified source of images, right? Perfect. In the next video, we're gonna take a look at these images, actually visualize them, and see what they look like, okay? And hopefully we'll see that 128 by 128 does not really degrade, or would not really degrade, the resolution of the images. Okay, perfect. I hope that this has been informative for you. If you have any questions, just post them in the comment section down below. And if you found this video helpful, feel free to like the video and subscribe to the channel. You can, by the way, follow us on Twitter, LinkedIn, and Facebook of MLDon. The links are again posted in the description below. I'm going to put this code back into the GitHub repository, and again, I'm going to put the link to the GitHub repository in the video. And remember, that's an ever-evolving GitHub repository, right? So I'm going to keep updating it as we go along with in this project. Right? And by the way, make sure you click on that bell-shaped button so that you'll be notified whenever I post a new video. I think this is enough, really. Okay, great stuff. Mind yourselves. Bye.